Hello viewers, welcome to Inspire Maths. I'm your host Idris, explaining continuity of modulus function in this video. But before we get started, subscribe to our channel by hitting this red button and click the bell icon to be the first to watch our new videos. So let's get started.
It is defined as f(x) equals mod of x. Mod x means that it will make every negative number positive number and every positive is positive. So it is defined as x if x is greater or equal to 0 minus x if x is less than 0. That means whenever we plug in a positive number there, it will give a positive number because it's defined as x when x is greater or equal to 0. For example, we plug in 2, it's defined as 2 because 2 is greater or equal to 0. And whenever we plug in a number which is less than 0, then it is defined as minus times that. So minus times that minus will make it positive again. For example, if we plug in minus 2 here, which is less than 0, then a mod of minus 2 will be minus times minus 2, it will be a plus 2. So f(x) is defined as x if x is greater or equal to 0 and minus x if x is less than 0. This is a piecewise defined function where the function is split into two parts at x equals 0. So if this is the real axis, this is the point 0. For x less than 0, it is defined as x minus x, and for x greater than 0, it is defined as x. So this 0 splits this real axis into three cases or three parts. One where we consider all the x's which are to the left of 0, another where we consider all the x's which are to the right of 0, and the third one where we consider 0 itself. So as discussed in the previous case, we will discuss its continuity for less than 0, greater than 0, and for 0 itself. So here we have case 1. Let me take a c, a real number, such that if I take any c to be a real number, either the c can be here or the c can be here or the c can be 0 itself. So either c can be less than 0 or c can be greater than 0 or c can be equal to 0. So with this we have three cases. The first case we will take as c less than 0. We know that continuity is defined as, if we define continuity, we have read it in the previous video, also in continuous function part 1, that a function so we have read that a function is said to be continuous at some point a if limit at a equals the function value at a. So when we had discussed the continuity of this function at c, we have to look at f at c. Since c is less than 0, so for less than 0 it is defined as minus times of x. So f at c will be defined as minus times c, so it will be minus times c. Also we have to look at limit x approach to c, fx. Now we know that this c is to the left of 0. So if we consider any x's which are to the left or right of c, all those x's will be left of 0. So fx at all those points will be defined as, whenever x are less than 0, it is defined as minus x. So whenever I will take any c to the left of 0, no matter how much close I will take it to 0, I can find x's which are very much close to this c such that those x's are less than 0. And hence for those x's, fx is defined as minus x. Therefore, when I consider limit x approach to c, if c is less than 0, fx, this will be same as limit x approach to c, this will be minus x, because I have to consider this part of the function. So that will be equal to minus c. So we see that the limit and the function value at c are both same. Therefore, we can write as this means fx is continuous at c. Now, there are more two cases when c is greater than 0 and when c is equal to 0. So let us discuss the second case. Let me take the case second here, c greater than 0. When c is greater than 0, that means c is somewhere here. In the similar fashion, as I look at f at c, since for c greater than 0 it was defined as minus x, but for c greater than 0 it is defined as x, so it will be just equal to c, and we'll just take a limit x approach to c f of x. Since c is now greater than 0, but for everything greater than 0 fx is defined as x, so it will be limit x approach to 0 of x, that will be equal to c, that will be equal to c. Therefore the limit and the function value at c when c is greater than 0 are same, therefore we can write it as limit x approach to c fx equals f of c when. So for c greater than 0, this limit at c is equal to the function value at c, therefore the function is continuous for all those values of c which are greater than 0. Therefore with these two cases, first and second, we have got that this function fx equals mod of x is continuous whenever this we have points left of 0 and right of 0. That means whenever we have points c which are less than 0 and which are greater than 0. Now we have the final case left, that is we have to consider the c equal to 0. So let me consider last and the third part. Before that, let me wrap out this. So here we have the third case when c is equal to 0. We note here that for right of 0 and left of 0, fx is defined differently. Therefore, when we consider this line and a point 0 here, we cannot talk of a limit at 0, because when we take the x's which are in the neighborhood of 0, that will include all those x's which are to the left of 0 and to the right of 0, but to the left of 0 and to the right of 0 fx is defined differently. So we have to take the left hand limit and the right hand limit separately and then see whether those limits are equal and discuss the limit of as a whole. So first we will look at f at 0. F at 0 will be equal to 0 simply. Now we will look at limit x approach to 0 negative, that means left hand limit at 0 of fx, that's equal to limit x approach to 0 negative. Now 0 negative means x's are less than 0, but for x is less than 0 fx is defined as minus x, so this will be minus x, but when we take x as 0 this will be 0. Similarly, when we look at x goes to 0 positive of fx, that will be equal to limit x goes to 0 positive. 0 positive means x's are greater than 0. For x is greater than 0, fx are defined as x, so it will be just simply x, that will be equal to 0. So left hand limit and the right hand limit at 0 are same, therefore we can say that the overall limit x approaches 0 fx equals 0. Also we see that the function value at 0 is also equal to 0. Hence limit x approach to 0 fx is same as f of 0, which implies f is continuous at 0. Therefore we got that this is 0 here. We talked about all the c's which are to the left of 0, and we got fx to be continuous for all those c's, and then we talked about all the c's which are to the right of 0, and we got fx to be continuous, and at exactly 0 fx is again continuous by case third. So therefore from all the cases, case 1, 2 and 3, we are getting that fx is continuous for all values of x. So here we can write finally fx is continuous for all x's belongs to R. If we look at the graph of fx, then we can draw the coordinate axis here. Here is the x-axis, here the y-axis, if we look at the graph of this modulus function, its graph is like this, just a V-shaped, which touches the x-axis at x equals 0. And we see that there is no jump or gap in the graph, and hence the graph is continuous. Thank you for watching this video. I'll be coming up with more interesting videos. Keep supporting the Inspire Maths. Thank you once again.